so I think Seogi is going to take the lead today and tell us a bit about compact norms and such. So Seogi, you're here and you're able to see and hear us?
Yeah, I think so. I'm not sure why my camera doesn't work, but anyway, that's fine.
Okay. Cool. Well, I'll hand it over to you.
Okay, so I'm going to
Whatever's on your screen. Thanks.
can you guys see my screen? Is that
projected up?
Yeah. Oh.
Thanks. Just make sure everybody's clicked onto Seogi's screen, and that'll make sure that you stay looking at him.
Keeps flashing in and out. I think we're okay.
You need to click on him, and that locks you on to whatever he's showing. Does that make sense?
Oh, okay. Oh, got it.
Yeah, well, not sure. Okay, I may not be the right person to talk about this, but I've been using like a DUMS sparse regularization, or what was IRLS, iterative reweighted list square. So DUM developed mostly for potential field problem, gravity and mag, and I thought like it'll be useful for EM inversions as well. So yeah, I kind of played with it for a while, and actually I'm using almost daily basis in these. So yeah, I guess just kind of want to share how I'm using it. Can you guys, is that okay?
Yeah.
Yeah. So
sounds like. John, sounds like it. So you can hear ourselves through your mic. Can you mute your mic? It's
my mic?
No, John. John. Yeah.
Okay, yeah, hold on here. Yeah.
Thank you.
Is that good?
Oh, that's better.
That's much better.
Right. So yeah, I just need to start from sort of inverse problem. You got a theta misfit term, regularization, and by using those two terms, we can set up an inverse problem. And the main focus is actually this phi m, which is a regularization function here. And that's where all the DUMS work kind of stays. Then I kind of want to comment about the linear and nonlinear inversion here. So for like a mag and gravity like problem, which is a linear inverse problem, E is equal to Gm. So G is the sensitivity, and M is your model. So for density, like for gravity, it's a density, and mag, it's a kind of magnetic susceptibility. And in the inversion, this sensitivity G doesn't change, so it's fixed. That's a kind of simple. But for like a nonlinear inverse problem, like an EM problem, or EC inversion or EM inversion, so now your forward function is it's nonlinear. So your sensitivity function now, it's not fixed, but it's updating in the inversion. So like if you got 10 iteration, each iteration have different sensitivity function. So that's a main difference. So I'm just starting with the difference and what we need to set up right to actually run the sparse inversion effectively for EM inversion or DC inversion. And well, this is the main term. Well, this is kind of simplified version. We usually have a smoothness and smallness and smoothness, but here it's kind of like a lump sum of both of them. And what's really important for EM problem is actually setting a right MREF. Because if you think about what we're saying, okay, we want to have most of our model parameters 0. That's what we're asking when we're using sparse inversion. So for magnetic inversion, it kind of makes sense. You don't really, your MREF is usually 0. Or for gravity, I think as well, I guess, your MREF is usually 0. But for conductivity inversion, like DC inversion, your MREF is not usually 0. So you have some background conductivity model. So you need to set that MREF really right to kind of like make it really sparse. So I think that's a very important point. So your initial MREF is very important. Well, like, if you guys have any questions, just let me know. Not very, it's not a very prepared talk. It's pretty casual. So here's an example. So this is an example that I used for a groundwater problem in California. So our background is about, our background is not kind of constant, but the first layer is kind of, it could be an aquifer, about 50 ohm meter. So this is the resistivity. We got a clay layer here, about thin clay layer having, I don't know, 5 ohm meter. And then we got another aquifer that's a little bit more conductive. I think the distinction here is water level. I think if you have a water level somewhere here, then you're going to get more conductive aquifer compared to the upper parts. And then you could have a very conductive basement, for instance. And this is the SkyTim data. Like, I'm not sure everyone knows the SkyTim data, but it's a dual moment, so you got a two waveform. And so you're going to get two decay curves as a data. So if I have a one sounding at this 1D layered Earth, I'm going to get these two sounding curves. So the orange one is low moment, and the blue one is high moment. So usually, like, this is normalized data, but if you actually plot the real amplitude, high moment will be much larger compared to low moment. And the idea here is high moment seeing deeper, so it can see much later time channel. Low moment can see the much shallower part. If I do the 1D inversion with that, this is what you get for L2. You're seeing the clay layer, okay, and both aquifer, you may see something reasonable, but the bottom part, you can kind of see something, but it's hard to say whether you see or not. Okay. Then if you do a sparse inversion, that's what you get. You're actually cleaning up all these structures, and then you're going to get very sparse. Here I set the kind of reference model as a 50 ohm meter. But if I set that at a 100 ohm meter or like different values, my sparse inversion will not be successful. That's an important point. You guys
Sorry, a couple of things. Seogi, one, is the only norm that you're using just that small norm, or do you have any smoothness in there at all?
I do have. So what I did, this is the code actually, and so for P is LPLQ. Remember that the P is for smallness and Q is for smoothness. So I think I used the Q for 1, and then Q has each direction, QX and QZ. But here I think that Z doesn't mean anything. Well, X doesn't mean anything.
And when you said it doesn't work because when you put in incorrect reference model, what happened? Were you able to fit the data, or you just couldn't fit the data, or that the model came out really crazy?
Oh, both. Like I think the model came out as like a very similar to smooth model, because how DUM is like kind of structured this sparse inversion. You first start with L2 inversion, and when you hit the target misfit, that's the point where you're searching for sparse models. If you use like a wrong reference model, or like, I'm not sure what's wrong, but like not proper reference model, you're going to stay in your smooth model.
Okay. Okay, go ahead.
Well, any comment, Dom?
No, I mean, you're right, man. If you start with the wrong model, you'll stay there. I'll be curious if you only use blocky, if that's not going to help you.
Yeah. So okay. So let's set 100 here and run it. What I did, I just set like what I used was 50, and I just set the 100. I'm running the code. Oh, I mean, this is kind of slow because of the Hangout. I think Hangout actually uses a lot of Yeah. So, well, it's not too bad. So this is what I've got.
So here your ref is too high resistivity. Is that what you're saying?
Right. Right. So I mean,
That actually looks pretty good. What's
well, I think it's like it's not. I'm not saying it's bad, but I think it's not sparse. So to make my point was to make your model really sparse. If that's what you're looking for, I think setting an MREF is very important. Still, when your MREF is a little wrong, you could do an okay job. But I mean, like, that's what I'm saying. Just like you need to set the like a proper MREF to get a really sparse model.
And can you shoot in the middle? So can you try 10 meters?
A 10?
Yeah, just for the kick. And all your time channels are all fitted equally, right?
Yeah. So I think, well, like my target, like I'm using the target misfit here, so it's chi factor 1. I think I used the 10%. Yes, your starting is actually a bit higher than before. Now it's 10,000.
And what's your strategy now, Sug? Are you fixing the sensitivities once you're passing to the sparsity?
Exactly. I'll explain that later.
Yeah.
So I think this one kind of like lines are broken. Yeah. So.
Yeah, it doesn't look like it did anything much, eh?
Yeah. So it's.
what's that?
Oh, sorry. This is sorry. This is L2.
Yeah.
And this is L like this is a sparse.
Well, trying to do something.
Right. It looks like you could work a little bit harder too. It's kind of stopping early. Can you see your convergence curve, Sug?
Not here, but I think I could. I need to rerun. Do that. Though. Right. Yes, I'm not sure. Like, so there's a save function, and with this one, you can actually plot the misfit curves and stuff. Like when it's running, I just got a quick comment about what Dom asked, because remember here, the nonlinear inversion, your sensitivity is changing. You need to update every iteration. But I was thinking, it's just a little bit of cheat, because let's say when you reach to a L2 solution, so now you got a model that fits the data well. So you're pretty close to the solution. So and then I think that I'm fixing like for this for the sparse inversions. That's the starting point. Your L2, a smooth model, and then that's your starting point for a sparse inversion. We're pretty close to the solution. So I was assuming, I don't really need to update the sensitivity. So I'm going to fix the sensitivity matrix. Although when I'm modeling it, I'm using the real model. So that's what Dom asks. In that way, you could be a little bit more efficient. And I found like that's actually fine for linear inversion or DC inversion.
Yeah, but perhaps only for a couple of iterations.
I'll agree there, because your connectivity is changing so much. Like, how can you justify this? I'm not entirely sure.
Yeah, could be. But it's very hard to measure that. But I'm just I'm based on the inversions that I've ran. I mean, it seems like
it's fast. That's for sure. So
that's pretty fast. Because I think that's a type kind of trade-off. I thought it depends, but sometimes it takes a lot of iteration. And if you want to do it for either DC or EM, that takes a bit of time.
No, I agree. For sure, it would be nice if we can speed it up. But yeah.
So in the implementation, do you have the option to do either right now, or is it always fixed based on?
It's an option, so you could do it if you want. You can update this. That's a misfit curve, and that's an option.
But when you chose that option, do you keep it throughout the whole inversion, or do you do it a few and then change back?
No, I think I'm just fixing for sparse update. After L2 inversion, I'm not updating the sensitivity matrix if I use the fixed J. So here, this is an option. So if fixed J matrix, if that's true, then I'm not updating. So, well, we could be a little bit smarter. Like at the end, we could kind of do one more step with using updating sensitivity matrix.
Yeah, you see originally in the minimum Gauss-Newton iteration, the options seg, I was using that to wait until the update of J. So you could always revert to that.
Yeah.
You know, do like 2 or 3 Gauss-Newton iterations fixing, and then you update, and then so you'll save yourself a few J.
Right. Right. So that's a possibility. So that's just an option. Like if you want to update, you could basically just say this is false, and it'll update every iteration. Yeah, and then if you actually drill down Dom's code.
I mean, another trajectory through here, Dom. I'm not sure whether you ever tried this, but if you're going from the L2 then to a different norm, let's say L0, I mean, you could actually step in successive iterations, to like L2, 1.5, 1.2, and sort of decrease the L as you're converging to whatever final value of P you want. I'm not suggesting that's a great way to go, but it might be interesting just to see how the program behaves and how what large changes you have in the sensitivity that are sort of preventing convergence.
Yeah, that's a good point. I think it's sort of what we're doing by cooling epsilon, because we're going from something that looks like an L2 to something that looks more like an LP. So we're sort of transitioning.
What did you say, Dom? I didn't hear you.
So Doug was suggesting to just march down the p-value slowly to where we want to go. And what I was saying is that because we're cooling epsilon, it's a little bit similar to Doug's idea, where we're transitioning from something that looks like an L2 to something that looks like an LP. That's all.
I see. Interesting. Right. Yeah, so that was sort of my experience. And one thing kind of cool, like this images. So the question, like somebody would question, okay, can we see a really deep conductor here? I think like these two images saying it's kind of hard to see, I guess. You probably need more other information to actually kind of resolve this conductor.
I'm curious, Sag, sorry man, interrupting again. Can I see your data fit? Can you show your data fit on this?
My data fit is pretty good.
The dots being the X being the real and the predicted. Wow, yeah, that's really good.
So, I mean, like, yeah, it's very subtle change, I guess.
So here's a perfect case for actually implementing various DOIs on this and showing, like, sorry, you can't see anything, trustworthy below 200 or 250 meters.
Yeah.
So I think here, if you start from 10 ohmmeter, it's kind of trying to go there, but I mean, like it's very subtle, I guess. So if somebody used the 10 ohmmeter, like initial, oh, they may see, oh, I can see that. Okay? But I think if you actually start it as 50 ohmmeter, that's what you will see.
Yeah. So like 250 meters is kind of your max resolution, right?
Yeah, yeah. So I think there's a value here, like a kind of what Dom you suggested in a consortium about like using different norms and kind of like having some sort of statistics for model credibility. Where like I wouldn't go to a model uncertainty. I think there's probably some value to it. So this is kind of simple example, but we could actually like use them more involved. And yeah, anyway, that's one that's a EM example, and this is the other. So this is the C1. So we got two conductor here, this one and that one. And I think the idea was the brine aquifer and freshwater. So this is smooth and this is sparse inversion. So it kind of works for DC as well. Yeah, and then here I think also setting a reference was actually pretty important to get a sparse model when I was trying. And then I also fixed the J. So I thought like, yeah, I'm not sure like what's the best way, but I think for me, kind of having an okay data, okay inversion reserve quick, fixing J seems like an okay, good option to use. That's what I thought.
Yeah, that looks good. I mean, hard to contradict you on that one.
So I think this is kind of a bit more, like I think you can if I push hard, I can go up to like this. So gotta reduce like two conductors, and I think this is chargeability. I did the IP inversion as well. I think this was true. I think it's more sparse than the true model, I guess.
And have you tried, man, to not do sparsity just blockiness, because then the reference model doesn't take into account anymore, right?
That's true. I haven't tried. We could try here. Yeah. So basically putting 2, right?
Yeah.
And I think there's a lot of, and what I'm excited about this. So like using actually in 3D inversion for like, for instance, DC, and also airborne EM and the types of like 2D and 3D inversion. I think it has a lot of value. And then it seems like other people are just doing on the smoothness term. That was my feeling when I was in some of the Aarhus group's research and stuff. So people are just putting on the smoothness. So they're basically doing a block inversion, I guess. They're not putting kind of sparseness in the smallness term. Is that correct?
Most likely, yeah.
Oh. That's a blocky.
Sorry, Simon, can you show me your log?
Log? Okay.
Yeah, this, yeah. Yeah, you need to let it iterate a little bit more than 10. It's okay, we can talk about it later.
Yeah, so I think that there's two things going on, right? There's the smallness and smoothness. So you can kind of like play with it here.
Yeah.
It's actually really nice. Yes, I really want to kind of use it in 3D, which I haven't really tried. 3D like DC and EM inversion. So that's probably my next step.
If you go back to the airborne case, okay. If you just let the sensitivities change as they would with each iteration and the change in M, did it just take a long time to go, or were things unstable, or what was the motivation
There
for?
were a couple of things. So Dom is doing the beta search. And I think, as far as I know, what he's doing is like he's comparing the target misset, and then I'm not exactly sure, but I think he's kind of like changing the beta value rather than like keep cooling it. And there are certain conditions like that kind of like that didn't really work for me. So I think I had to always kind of fix the beta. I'm not. Dom, can you help me? I think I'm not sure where I'm going. So what I had to do was that beta search false, using the beta search false. I think that was important for me to make it work for EM inversion.
What does the beta search do?
Yeah, so beta search is just an intermediate step. If you're too far off the target, it will just look for the right beta and then keep the model the same. That was the idea, but might need more testing.
Yeah, so that one actually it makes it quite slow. So.
Oh yeah, it will be slower, yeah, because you're doing multiple inner solves, right? Without doing any work, you're just looking for a right beta, basically.
Yeah, so sometimes like it just break there. So I think like here, what I had to do, I had to just like make it false. And then then I'm keep cooling the beta. Is that right?
Well, can you look at the log again? I just want to know. I just want to see if it goes up or down, or if it's.
I think it goes up or down.
Okay, that's good. At least it tries to shoot.
Yeah, so I think it's not meaning I'm always like a decreasing beta. It still does the scaling. But I think this beta search step is more like a kind of line search like a kind of step.
Yeah.
Where you,
yeah. You just fix it until it finds it instead of marching on.
Right. Yeah. So Doug, my answer. I think the reason why I fixed J, I think that was mostly similar. The result that I've got was pretty similar. But the example that I have tried is kind of limited, so I'm not sure that's really general case.
Yeah.
But yeah, I think I don't think the sensitivity changed that much. I guess once you're close to L2, that was my feeling.
Well, I think if you looked at the very end with what you've got, and then looked at those sensitivities and compared those with what you had from the L2, I mean, that would be interesting to see how much change there was.
Right. So, yeah, I think that's it from my end. And oh, right. I just wanted to show you guys one more. Didn't have the time to prepare. So this is an example that I've used for Doug's keynote in Denmark. Here, what I did was actually using kind of three different data sets. One is frequency domain resolved, and the other geotem time domain TM. And the final one is ground TM data called nanotem. And so this is a model. So what I'm trying to do here, okay, I got three different data sets. I want to invert jointly. That was what we did. This is the structure, conductivity. We got a near surface resistor up top, and then deep conductor. So I think all of this code is actually running each inversion, separate inversion, and comparing at the last. So I think this is the smooth inversion resolve. So resolve is frequency domain system. It's very sensitive to near surface compared to time domain. You're seeing a near surface resistor well, not kind of. You can see the existence of it. And then geotem time domain system, you can see deeper, but the near surface resolution is kind of worse compared to resolve. So you're seeing the deeper part well, but not the top part. And the nanotem is the ground system, so it has the kind of strongest sensitivity for the near surface part. So you can see that near surface resistor pretty well, but you're putting some artifacts at that. Now you invert them jointly, so you can see all of three jointly. So what I think that's probably, yeah, I think this is actually an important term. So can you guys see that? The misfit is equal to time domain, frequency domain, and ground. This is basically what you need to do for joint inversion. So you just need to generate three different problems, generate three different misfit, and then sum that over. So here we're using Lindsay's combo objective function, which is actually pretty cool. And then you can do the same thing for regularization. So I think right. So here we don't need to do anything for regularization, right? So we got just one conductivity, so we don't need to use the combo objective function. Okay. So we're inverting for a single conductivity. Now I'm going back to joint. So that was actually joint inversion result, which is pretty cool. So you're kind of like getting all the good things into if you're using joint inversion. Then this is actually a L0 result. So you're getting sparse model for resolve and geotem and nanotem. And this is the joint inversion with sparse. So that's actually like kind of nice. Yeah. I think it's all the functionality we're getting. So we can actually do joint inversion for inverting for single conductivity, which is pretty exciting. And this is a simple example for 1D, but at least we got the structure, so we could actually run 3D later. We haven't got the kind of actual capability to do it. But,
that looks super good, man. Did you have to do any fudge factor between your surveys, or?
No. I think yeah, I didn't use any. I think it's basically just no fudge factor.
Nice.
Yeah, yeah. So I kind of carefully designed the survey. So I think I chose a system that they can help. That's the only thing that I did. Like, so each survey have some pros and cons, and then by summing all three, they kind of like compensate each other. That was actually what I did, but I didn't use any fudge factor. Which actually I thought cool. It's fairly robust, I guess. Yeah, so I think that was about it from my end about my experience about using sparse inversion. Yeah, so that's actually really cool, and I'm actually pretty excited to use more and more. Thanks, Dom.
Well, I'm excited about what you're doing. That's awesome.
Okay. Yeah. So Tom, one thing. So I made a pull request. So I had to change a couple of things in your code.
Okay.
If you can take a look, basically like this part. So I think I made a comment here in the directives.py.
Yeah.
So I had to kind of remove some if statement. But yeah, if you can take a look and make some comment. The test is failing. Some of your test is failing, so I wasn't sure why. So if you can take a look.
Okay.
Yeah, I kind of want to merge this as soon as possible because we want to make all the notebooks that we use for Airborne EM course available soon. So I think this is one repository that I use for that. Yeah.
My tests are failing, you're saying?
Yeah, so I think in some gravity and mag inversion, I think it seems like you're testing the sparseness. So I think that's where the tests are failing.
Yeah. Okay.
Yeah, so I think probably what I've changed it probably screwed things up a bit, I guess.
I'll look at it. Yeah, no problem.
There were a couple tests, I think, not too many.
Oh yeah, and you saw that one. Did you change it back about the power 2 for the sparse matrices?
No, I think the only thing that I changed was power 2, but I just changed it to star 2. So
No, that's the thing. Is it's new to SciPy. If you want to do like a element-wise operation with sparse matrices, you need to use power. Otherwise, your memory is going to blow up.
oh, really?
Yeah, I looked it up and.
Oh, okay. Yeah, I didn't know that. And then I think I was having errors somehow with that line. That was the only reason I changed it. But yeah, I probably need to update my SciPy then. Is that like a latest SciPy?
Yeah, that's the search. That's what I found on the search, because I was getting memory issues on my side, and then that's the answer that I got from the great internet. You need to use power too if you want to do element wise.
Oh, but I thought that even if you put a matrix, if you do dot dot star, I thought that they are doing element wise operation. Is that wrong?
I can look again, but according to what I found, and it worked for me, my memory stayed stable if I was using power 2 instead of star star. But
oh, okay, I see.
we can double check.
Fine. The only reason I changed it because I was getting errors on my machine, so that was the only like reason I changed. But yeah, I could update my SciPy. Okay.
Sounds good. We'll merge it in, man, soon.
Sounds good. Thanks, Sam.
That looks great, Seogi.
All right, there's a couple things to share. I will share my screen here in just a second. There's a couple updates to SimPEG just with the most recent releases that I'll share with you. And then there was a call. One of Rosemary's students, her name is Meredith, she is interested in doing DOIs for airborne EM. And we just don't have any examples right now. And so I was wondering if somebody would be game to create one, if there's something that's relevant to what you're doing. It doesn't necessarily have to be EM, but if it would be helpful for us to have in the docs anyways, I think. So if you're interested in doing EM, that would be great. But if not, if there's something else relevant to what you're doing and you want to take that on, that would be awesome. So she was going to write up an issue. I haven't seen it yet, so I'll ping her today and we'll see if we can get that written up, and then somebody can take that on if they're interested.
Yeah. I'll try, Lindsay.
Okay, that'd be awesome, Seogi.
Yeah, I think I got some stuff, and then I need to do that anyway. So, I'll do that.
The example that you just did is a perfect format for just trying this.
Yeah, yeah. So I'm like I just wonder how far we want to go. I think depth of investigation is kind of like a very limited kind of aspect, because it's more like I don't know how certain you are on the model. Anyway.
But I think that just providing something that can produce a result that is just somehow quantifies how much currents are going down or how much change you're getting when you just change the the background conductivity or any of these things, and then not put it forward like, okay, this is how you calculate the DOI, but these are things that if you're going to calculate a DOI, then these things might be useful. And if you want to set up a threshold parameter on what you can see or not, then that's fine. We don't care about that. But just to take and kind of try to codify a little bit that non-uniqueness, and where you can change the model at large values at a particular depth. I just think just something along that line would be useful.
Right. Yeah. I'll think about that and put something together.
Yeah, and I think that's all she was asking, is just like, if we have, an example of one way to do it. There's certainly plenty of ways to go about calculating a DOI, but, if we've got one way that we can put forth, then that's helpful for people.
Sounds good.
Cool. Okay. The other update I wanted to share is a contribution from Dieter. So this he originally implemented in EM-PyMod and has adapted to be suitable for SimPEG. And so what this is if you now run simpeg.versions, this is a really good thing to do at the end of any of your notebooks that you're distributing. Because what it does is it actually shares what your environment is. And so if you want to actually have somebody reproduce your results and you can see that you are on SimPEG 0.8.3, you can see discretize, and then all of the dependencies as well. So something like what Seogi and Dom were talking about with SciPy. So if you actually want to see if there was a change or if you guys are running on different versions and that's what's causing the problem, this is like a very transparent, quick summary of what your environment is that depends on, or that SimPEG depends on. So he's got a nice version that prints nicely in HTML in the notebook, but it also runs and will print in a Python script in plain text or in an IPython kernel. So if you do without the HTML tag, it just prints in plain text. And then if there's other stuff that you've imported that's important for your analysis, like maybe you're using scikit-learn or something like that, and that's really important for what you're doing, there's docs on how to actually like add that to the listing. So all it does is imports it and checks the version and prints it.
How would you protect this? Because let's say I give you a notebook that I've run on my computer.
Yeah.
If you rerun it on the computer, it's gonna reprint over.
Yeah.
Yeah.
I mean, it's the same thing as like if you're sharing notebooks via version control, stuff's gonna change, but at least like
there's a way to do it.
There's a way to, yeah, there's a way to do it. And, you know, first thing I can just glance at what you did and I can always hopefully go back to the email or Slack.
Sure.
Or whatever.
Yeah.
So, yeah. Yeah, but I would recommend for anything that you're sending out for publication or stuff that you're pointing people to in repositories, just add this to the end of your notebooks.
Yeah, that's really nice.
Awesome. Yeah, so you can send a shout out to Dieter for that.
Yeah, it seems working.
That's in SimPEG 8 or 0.84. And then there were some small updates to just the way we're storing inner product matrices for the EM code. So try and hit on that. And if you see anything funky going on, let Seogi or I know and we'll dig into it. But it was a pretty minor change. Then there's a few other pull requests we'll try and get in. So we can take a look at, once Dom's gone through this, just maybe ping me, Dom, and I can try and do a pass too, and we can get it in pretty quickly, because it doesn't look like it's a big pull request.
Okay.
The 3D Sill stuff I'm working on trying to get in. I ran into some issues just with versions of properties. Franklin's gone in and looked at that, and so I just need to figure out what he figured out, and then we should be on the same page. And so once these two pull requests are ready to go, then we're actually in a place to merge in the 3D Sill code in discretize. And so there's some changes I made in discretize that require that we make updates in SimPEG. The biggest thing just being that the CellGrad stencils are properties rather than methods. Mm-hmm. They should have been properties in the first place, but we missed that. And so everywhere in SimPEG, there's brackets right now. And with that pull request, I just put in that fix. Should have done it separately, but oh well. So once all of this stuff is in shape, then we can get both of those in, because they sort of have to follow one after the other. So are there any other pull requests people want to go over here right now? I don't know too much.
Really, I think any changes I'd make to my stuff, I was going to wait until the simulation was brought in, simulation class.
Let's take a look, because the simulation class is going to be a while.
Yeah, well, I don't think there's any rush on VRM stuff.
Okay.
I think I'm the only one who's looking at it, so it can kind of sit there until you feel like getting at it, or until it's a good time. So.
Okay, that works.
Should revise the potential 3.1, just go back and I mean, it was just a few changes, so it's, yeah, I think that should be cool. That should be good to revise, and then if we get this done, go quickly over and was like some stuff on it. I remember I was the precondition, something on the precondition aside, and some naming convention to a consistency between grab and bind.
Okay.
Would you guys be okay if we start using the parallel part?
I think. So, are you looking at multiprocessing or DAS?
Multiprocessing. Yeah.
Multiprocessing.
Yeah.
Yeah, I mean, I think that's worth starting to bring in, as long as it's like clear how especially Windows users can use stuff. I mean, multiprocessing is core Python, so I don't think there's a problem in starting to hit on that. Yeah, so let's just maybe before it goes like too deep, if you have an example that it's running on, if we can do a quick PR review, even if it's not ready to bring in, just like we can look through the implementation and give it some thought.
Yeah.
But
okay.
Yeah.
We don't have to either. Yeah, that's good.
Cool. Then the only other thing, we're gonna create some issues on the apps side of things. So for the Houston course that's coming up in a couple of weeks, we're hoping to make heavy use of the apps, so way more so than the disk. Like the disk we sort of showed people and demoed a couple. This we actually want to have people using it, like using them every day, and hopefully we'll sort of get almost all of them used. So there's a couple small adaptations that we'll be looking for, and potentially the addition of some apps. But the biggest thing that I think we'll ask for help on is just extending the current ones. So we'll get some issues written up, and then if people are willing to jump in and help, hopefully none of them are too big. So it hopefully should be just like, you know, an easy thing to knock off in an hour or two. So if somebody's willing to take those or take a chunk on, that would be very helpful. Distribute the workload. So. Okay. Yeah. Doug or Seogi, did you have any comments on that or things to add there?
No, not particularly. I think the course that's going to be offered in Houston really does take everything to a new level compared to the disk, because we really get to work in depth with the apps. But the other thing is also really trying to see how we truly integrate, you know, the apps and GeoSci and all of, you know, the GeoSci elements kind of in one kind of seamless, holistic model. And yeah, so we're kind of developing that at this point, and it's, you know, probably going to require some kind of, you know, refactorization of you know, of GeoSci. But in the interim, just being able to, you know, have the apps, use them, connect up with material in GeoSci at different levels, and all of the case histories and the geophysical surveys, just to be able to kind of somehow, you know, walk through that seamlessly and have the user become familiar with all parts of that. If we could accomplish even a good step towards that final goal, I think we'll really have something that's going to be useful.
All right. Any other comments, questions, things for today? No? If not, thanks, Seogi. That is very exciting to see. And it'll be fun to get that pull request in and start playing around with different norms in EM code.
Cool. Thanks, guys. And Dom, I'm going to be in later this afternoon. Are you around?
Oh, yeah. Wait. Perfect. Anytime.
Okay.
All right.
Okay. Thanks, Don. Thanks, guys.
Bye-bye.